Horizontal axis wind turbines, commonly used for power generation today, are more efficient than vertical axis wind turbines, but have their own set of drawbacks. Vertical axis wind turbines are becoming more popular due to their low noise levels and ease of maintenance. Recent studies suggest that they can generate more power per unit area, which makes them a great choice for efficient land use. In a wind farm, the wake created by upstream wind turbines significantly affects the performance of downstream turbines. Studying this effect through wind tunnel experiments is challenging because it's hard to replicate real-world turbulence in a lab setting, and field measurements don't offer the controlled conditions needed for precise analysis. This study, using the Neurion supercomputer, aimed to understand the flow structures around vertical axis wind turbines and to predict how turbines might interact, as well as their power aerodynamic performance for future wind farm construction. The research was conducted in a turbulent region where pressure and velocity fluctuate rapidly over time and space. Studying such a realistic turbulent environment enhanced the accuracy of our analysis and predictions. In fluid dynamics, the Reynolds number, the ratio of inertial forces to viscous forces, is a key parameter for determining whether a flow is turbulent. At high Reynolds number, flow needs to be resolved with dense grids over a large region. To simulate turbulent flows within a wind farm, the present study over 15.3 billion grid points at a Reynolds number of 80,000. This required simultaneous use of 1,500 nodes on the Neurion supercomputer for the calculations.
네, 수직적 풍력 발전기 주위에는 굉장히 복잡한 난류 유동이 존재합니다. 이런 난류 유동을 파악하게 되면은 그 발전기의 효율을 높일 수 있을 뿐만 아니라 발전기 단지에서 발전기들을 어떻게 배치하는 데에 큰 도움이 됩니다.
Professor Choi and his research team at Seoul National University simulated three-bladed vertical axis wind turbines to analyze airflow and identified forces exerted on each blade. The team used the lambda-2 value to confirm periodic turbulent flow structures at the leading edge and tips of each blade during turbine rotation. They identified the tip vortex, a small vortex at the blade tips, and the leading edge vortex, a dynamic stall vortex at the blade's front. Through their analysis, they could observe the dynamics of these flow structures, which have a significant impact on the blades. Here is a two-dimensional cross-sectional representation of the airflow. You can see the small flow structures forming at the rear part of the blades. Notably, when a blade is closest to the direction of the wind, a leading edge vortex forms at the front part of the blade. The leading edge vortex and the tip vortex are observed more clearly in the flow structures at various blade positions. The generation and interaction of the leading edge vortex and the tip vortex can lead to blade instability and degrade turbine performance. Although the leading edge vortex generally appears along the blade, it is suppressed near the blade tips due to the influence of the tip vortices. This interaction is also visible on the isosurfaces that represent the regions of low pressure. The research team also investigated how the wind flow changes behind wind turbines to understand the mutual influence between turbines. They found that the rotation direction of the wind turbines and the flow structures lead to asymmetric wake. To study the impact of these changes on downstream turbines, the research team conducted a CFD analysis on a large-scale wind farm with 2 rows of turbines. By rotating the adjacent turbines in opposite directions, they were able to increase power generation efficiency. Then the team compared the overall efficiency of the wind farm between 2 configurations: a non-staggered arrangement with the second rows of turbines directly behind the first row, and a staggered arrangement with the second row positioned between the turbines in the first row. To determine the changes in wind flow, the flow velocity was visualized in 2 dimensions at the midspan of the blades. In both arrangements, the turbines in the first row rotate in opposite directions, creating alternating regions of severe and mild velocity reduction between the turbines. While the impact on the second row turbines is uniform in the non-staggered arrangement, the efficiency drop is more significant for the turbines positioned in the regions of severe velocity reduction in the staggered arrangement. This led to the conclusion that the non-staggered arrangement is more efficient for a wind farm. In this study, the research team established a mega-scale CFD analysis code on the Neurion supercomputer, allowing them to analyze flow structures and velocity reductions around and within the wake of vertical axis wind turbines. Their performance analysis provided valuable insights into the most efficient layout of turbines in a vertical axis wind turbine farm. This research has produced various academic benefits by enhancing our understanding of the factors affecting vertical axis wind turbines, and it has also achieved significant results with potential industrial applications.
도심 환경에서 사용이 가능한 다양한 형태의 수직축 풍력 발전기를 개발하기 위해서는 여러 발전기가 동시에 작용할 때의 세밀한 유도 영상을 파악할 필요가 있습니다. 본 연구에서는 슈퍼컴퓨터 누리온을 통해 10만 개의 코어를 사용해서 정밀한 해석을 하였고, 이를 통해 발전기 해석에 충분한 가능성을 보여준 부분에서 큰 의의가 있다고 하겠습니다.